the chiral elastic metamaterials.
Yes.
Have you looked at the anisotropy of your systems?
Yes, I mean we tried to. I mean the structure in itself is prepared in a Duraform, which is an anisotropic material. So its constitutive matrix is anisotropic. What we have not done yet is to see if there is the possibility to find a kind of homogenized material that could behave in let's say in this non-trivial, non-Cauchy media way.
Okay, and I've got a second question. It's regarding the last part of your talk.
Mm-hmm.
You perform the modeling because it's coupled electromagnetic elastic system. So how do you model that?
The photoresponsive.
Yeah.
No, the photoresponsive is not coupled at all. It's a contactless structure. So basically, it's a aluminum plate with pillars that are 3D printed. But instead of using ordinary pillars, ordinary polymer materials, we doped this polymer with a molecule that is photoresponsive. This means that if you illuminate with a light at specific wavelength, it rearranges somehow its molecules so to change the mechanical properties. So the idea is that you avoid at all kind of electromechanical coupling or other kind of stuff, but you directly illuminate with a laser a specific portion of your structure. The mechanical properties of this structure changes, and the overall frequency dynamic response of the structure changes.
Okay, but your elasticity tensor is affected by light. You have an input in your system.
Right.
So, how do you take this into account? I mean, so you can switch on and off light.
Yes.
The properties of your elasticity tensor.
Okay, are you talking about the modeling?
Yeah. Yes.
Okay. In the modeling, it was seen that when the light was illuminated, it produced a 28% of Young modulus value. So basically, what we did in the numerical simulation was to reduce the stiffness matrix of 28%.
But it's some kind of phenomenological model. It's not.
Yes. Yes.
Okay.
May I ask a question, Sebastian?
Yeah, sure. Of course, please go ahead.
Yeah, actually, it's regarding this model, this material, where you said you are doping the material with some other polymers, right? With low or a very high concentration.
The concentration is. I don't remember by heart. It's not extremely high. And it should be, I guess, reported in the paper, but I don't think it's extremely high.
And when you put the light on, it's a polarized light, or it's anything? You just put a laser, anything?
Yes, we just put blue light at a specific wavelength, and this produces this rearrangement of the molecule.
And you observe a static increase of 20. You said about 30%.
In our case, in the specimen that we used, it was 28% or roughly 35. I don't remember, but it was, let's say, around these numbers of decrease of Young
decrease.
Decrease.
Okay.
And
decrease.
In the dispersion, let's say in the frequency response, we can see that the bandgap shifted towards lower frequencies. But let's say the group we are working with, they were also able to observe an increase of the Young modulus.
But with some other material.
With other kind of, yes, different type of.
But actually, how long do you heat? I mean, are you heating the sample at the same time?
No,
or it's just...
Sorry, I apologize for this because I have not been. I'm not talking about the transition temperature. So basically, we are well below the transition temperature. So we heat up a little bit the material, but we performed also DMI, dynamic mechanical analysis, in which we verified that indeed the temperature that we reached in the materials were not enough to justify the decrease of the Young modulus as if it was only for heating. So I would say that we do not exclude, indeed we measured a certain heating in the material, but we are below the transition temperature. And this is also visible from the fact that the recovering time is like less than 1 minute, is 45, 48 seconds. So of course there is no time to the transition temperature to liquefy the polymer. We have also tested it for 100 cycles. So it's really, I guess, the main the driving issue is the photosensitivity, and well, of course, there is a little bit of heating that would be responsible for a minor modulus change.
Can I ask something along the same lines?
Sure.
So, what determines the time scale of this photoresponse?
The way the polymer is prepared. So how much it is doped, the way it is done, and also.
Sorry, I mean, what physical mechanism determines the time scale?
I apologize for this, but I mean, I am not the one who treated this. So I prefer not to say something that is wrong.
I'm asking because you talk about order 1 minute timescales. And
yes,
this smells to me a lot like this is a thermal process in this polymer, which has a very small heat conductivity.
Mm-hmm. I mean, if you don't mind, I will get back to you once this investigated and better clarified, because the risk now here is to say something that is not perfectly true, and I mean, I apologize for this.
There's a question that, of course, is on people's mind is, I guess you're planning to look at the rainbow effect by varying the height of pillars.
Yes, this could. I mean, the next steps could be indeed examining different kind of geometries, but like producing a way to control in a more selective way the light. So we could imagine that if now we just have irradiation of a specific area, we could find a way to manage to illuminate the sample in a more constructive way, in a more, let's say, complex way.
Okay, so any more questions? Bogdan?
May I ask another one?
Yes,
Sure.
of course.
In roughly in the middle of the presentation, you said something that you were pressing on the sample to change the band gap, but I missed. I mean, it was changing by roughly a few percent, but how much are you pressing on the sample? Is it like deforming the sample by 5% and getting the band gap changed by?
No, sorry. So maybe it was this one. Can you see my screen? Yes.
We see your face at the moment. You have to share it again, I think.
Sorry. Yes, I share again. Share. Okay. Do you see the screen? Yes.
Yes.
Okay. So I guess that you were mentioning this slide, right?
Not that one, but if you go, it was.
I have to go up or down?
I think go further.
So up.
You had the overlap of two dispersion relation with a shift to the lower frequencies when you.
Yes, so maybe maybe someone of this one. This one?
No.
No. Maybe this one? No.
No, sorry. Then I will come back to the question another time.
No, I apologize. I didn't put the slide number on all the slides. Maybe it was the only thing where I remember that there was some pressure was this one, but actually on this one we were measuring the stiffness of the two samples. So the one, the syntactic, and the one isotactic. So when there was mirror symmetry or not, and this was to kind of prove that the two specimens had the same stiffness, but they dynamically behaved quite differently.
Okay, thanks.
Thanks to you.
Any more questions?
Hello, do you hear me?
Yes.
Yep.
Yes, Marco, thanks for the presentation.
Thanks for listening.
I have, how come, please, that when you take the smallest cross and you apply block boundary conditions,
yes,
and you take the huge one, you don't have the same band gaps. Can you get back to this slide, please?
Yes, sure. Okay, so
because you are talking about flat bands. These, yeah, the other one.
This one.
The other one.
Okay, so this one basically it is the big cross. This is a comparison of the big cross that has the same size of the hierarchical, but it has no microstructure.
Yeah, I understand this one because you are soften. In fact, the
exactly.
Yeah, and all the bands will go to lower frequencies. I understand this one. Yes. Even I have for this one I have another question. If you, for example, if we zoom up to the upper edge of the Bragg band gap, almost we will have the same behavior as what you have in the homogeneous case. The same bands, not the same frequency, but we will have the same behavior. Yeah. Apart this flat band inside the band gap. Yes. Can you please give us an insight about the localization of this band? Because for me, I didn't understand where it comes from.
Sure. So maybe in this case, I do not have the dispersion modes, specific dispersion modes, but I can explain you with this other model. So yeah, sure. Basically, you see here, there is a similar situation in which we have a band gap, and then we have a flat modes, which is localized, the indices of a localized mode that comes into the system. And if we give a look to this mode, this one should be, I move your face because it's on the screen. So like if we give a look to this one, this is a localized mode that indeed is achievable thanks to the additional resonator that it has been introduced in the system. That's why
I agree with this. I agree with this case, but with the other case, it's a little bit weird because in this one you have a tiny resonance inside, but the other one you have, for example, why I am saying that, because we are still compared to the tiny crosses, we are still long wavelengths.
Okay,
do you understand what I mean?
You're talking about this mode here.
So to me, this mode is a little bit weird to have. I'm really curious to see where the energy is localized for this specific mode.
I now see the question. Sorry for not having understood so rapidly. I can tell you that to my feeling, I mean, I do not have a direct mod shape of this mode, so we cannot exactly see how it looks like. But I would say that the first branches, which are this one and are the mod shape that I presented, they shift due to the change of stiffness. Okay, this mode, maybe, I think that could, a process that is very similar to what happened in the other structure where the inertial amplification was, it could have been happened. So basically that due to the more compliance of the structure, there is a mode that before was at higher frequencies that somehow has been shifted towards lower. But for sure, the best approach is to directly go and look how this mod shape looks like.
Okay, so back to my first question. When you have these flat, in fact, these flat modes, they are just coming from band folding. Do you agree with this? Because
it could be, yes.
Yeah, you are taking this from a supercell configuration.
Right. In some, yeah.
But the problem here is when you are taking a supercell combination, this supercell technique, you should end up with the same band gaps. This is what I didn't understand.
The problem,
so for example,
yes, no, the problem, I think that it comes from the fact that this is an atypical supercell. So this means that it's not only a straightforward band folding, to my understanding, because of course the little cross, let's say, feels about the fact that there are free boundaries or not free boundaries, and so I suspect that it's not only due to the band folding, but is rather I would not say independent mechanism, but it's given by the structure, the architecture of the complex architecture of the structure.
But do you agree that when we are basing a study, we are basing almost on the band diagrams? So here, you tell me, can you correct me, please, because I'm a little bit mistaken. It's like you can say, for example, if you take this technique, so you will find band gaps, and if you take the other technique, so you will find no band gaps, and this is bizarre.
No. Why you say that you would not find the band gap?
Because you said if you take the second hierarchical, it is the same structure when this one and the other one just with the next slide.
So you are comparing this one and this one, and this one.
Yes.
So no, this is no. Sorry, maybe it's the problem due to the quality. But this structure is a ordinary cross-like holes. So this is a square with a cross-like holes inside. This one, there is a cross-like holes here, but there is also a lot of very small cross-like holes here. So the two band structures, it's. I mean, I would expect not to be the same.
So the previous slide, what is the structure? This is just.
This one, once again, this one is the small one. So this one is the green. You see, first structure or first hierarchical level. So is this one.
Okay.
This one is the second hierarchical level. So is this one, the big one. But
so we end up with the same as the next slide.
So this structure
and the other
is
one.
The same of this structure.
Okay. So why do you
what changes is that here the diagram goes from 0 to 750 kilohertz, and this one is a zoom going from 0 to 40.
Okay, sounds great. Thank you.
So what would be your guess if you now have many more scales? So far you have 2 scales, okay? But you can imagine some kind of iteration and then you get 3, 4, 10, 100.
Yes. Actually, we are working on a kind of homogenization approach because of course, if you go straight with the finite element models, you will very rapidly need a huge quantity of memory, and the calculation will be, especially for the 3D case, will be just insane. But what we are trying to do is to homogenize like the behavior of the small cross and to add it recursively in the next dispersion diagram, so that you do not have to discretize the whole structure, especially because you will be at lowest frequency. And my idea is that at each hierarchical level that you introduce, you will for sure introduce higher frequency band gaps for which the small cross or the small hierarchical level will be responsible. And in addition, continuing lowering down, if you lower the stiffness of the structure, lowering down the band gaps and adding other flat bands in pass bands in other structures, in other band gaps.
So here, regarding the homogenization, so it's called reiterated homogenization. You have 2 possibilities. Either you have well-separated scales, or you don't. And I can see that you have looked at the 2 aspects. So before, in one of your slides, you had some kind of tool scales, but which were not well separated.
Yes.
And so what is your tentative plan? You want to look at well separated scales, or
the first attempt maybe will go through well separated, which maybe could be more straightforward. But in the case the not separated could provide better solutions, we could explore also this one.
Can we just go back to the case? You had a slide on the 2 possibilities.
This one?
Yeah, because in one case you have the viscoelastic model. So now, so the viscoelastic model is when the scales are not well separated, isn't it?
Yes.
And so, so this model, when you would have many scales but not well separated, would lead towards a highly viscous medium. That would be the guess. I mean, it would be.
I would say yes, because indeed, when you introduce viscosity, and if you take into account the imaginary part, you can also imagine one thing that I have not here the slide, but one nice thing that I've done is like if you plot these curves, and instead of plotting by color, you plot it as a scatterer, where the scatterer is the highest the imaginary part is, and the more the color goes to white, there will be some of these branches that simply fade away. So as you were saying, and as I said in the presentation, many of these modes that we can see here, because the analysis was purely linear elastic, would disappear. So this approach will allow to further increase the potential, show the potential of the hierarchy, because indeed what we see here as partial conservation of band gap, with many hierarchical levels, you will increase the imaginary part of the wave number, and of course you will tend more towards a total band gap conservation, in addition to other band gap opening.
So the lucky guess is that in the case of not well separated scales, when you have an infinite number of scales, you end up with a highly dissipative medium, which would in the limit just dissipate.
Yes.
Something like that.
I would say yes.
Okay. Are there any more questions?
Can the diode theory apply to what we call this porous media? Porous media can be linked to what you are doing, Marcos?
Yes, I think that if you give a look, especially to the different scale levels, like for example this structure, we really go in the direction of a porous structure, and even in the biological systems that you have in nature, the hierarchy often brings to porosity.
Okay, thank you.
In fact, I guess that in the limit, if you don't have well-separated scales, you might end up with some kind of problem where your partial differential operator has fractional derivatives, something like that. No, this is not.
Yeah, it could be.
Because in fact, what do you have in mind with COMSOL? So you're going to implement the limit problem in COMSOL, you're going to perform the asymptotic analysis, and then you're going to implement the effective medium as a result? What are you going to do?
No, well, the idea was to obtain effective properties of a hierarchical level and then reproduce the next one in the next scale.
Ah, I see. Okay, so you have an effective medium description of the large scale, which you then, yeah, okay. No, of course, yeah. Okay. Yeah.
The experimental part, Marco, when you take just one line of big crosses and tiny crosses for the experiments with the transducer, lynching, all types of elastic waves. This one.
Yes.
You weren't surprised by supplemental modes because you are taking a beam over here, not a plate. So for example, just to clarify what I mean, instead of having one quadratic mode starting from gamma, you will have two modes, quadratic modes starting from gamma.
Yes, I don't know if here I report from 0. No, this is not 0. But indeed, what we did here is to reproduce the calculation for the full 3D model instead of using the plate one, because of course the boundary conditions, especially here and here, will matter. And so to avoid discrepancies between the model and then the experiments, we took into account this fact, and indeed
so you didn't take periodic boundary conditions, you changed it from to freestanding boundaries.
Right.
Okay, thank you.
Thanks.
There is a question from Antonio. Actually, not a question, but an answer. And Bogdan, if you can open his microphone, it would be.
I did already. Antonio, your microphone is on. I don't know if he is still with us.
Okay.
Anyway, if not, I have a small, very. First of all, thank you very much, Marco, for this presentation. And this is in this model. You have time, so you have a time-dependent analyze, or do you hear me? I don't know if my microphone is on. Yeah. I don't know if Marco hear me.
I hear you, but not very well. Hello?
Yes. So
just a
if
quick
you
question: if you have a time-dependent analyze in the case in the elastic case.
No, sorry, I didn't get the question.
It's a time-dependent analyze.
In which case? In the viscoelastic?
With the plate, yeah. With the crosses.
No. This one. So this one are measurements, and this is block
No,
flocking.
no.
We can't see your screen, Marco.
Oh, sorry.
Screen.
Sorry, I start sharing again.
The numerics of the.
Okay, so I'm
process preparations.
sharing the screen. Now you should see the screen. Okay. So Bogdan, you were talking about.
So the perforations, the cross perforations you have in the plate, but the numerics it's a time dependent analyze.
No. So this one, let's say the dispersion curves.
Yes.
In this case are just linear elastic problems. So standard block flocking without adding any dependence from viscosity, frequency, or time. Instead, in the next session, this one, the calculation were made with assuming that the stiffness and mass matrices were frequency dependent, and so there was like the imaginary component of wave number that could have been calculated.
Okay, thank you. So I don't know if you can answer, Antonio, maybe.
Yes, okay. I'm sorry, but I lost the connection because yes, I have a bad connection at home. But the question was about the thermal effect on the photoresponsive material, is correct?
Yes, we were two to ask that question. That basically the change in the property is probably due to the temperature and maybe not to some other effects. Okay.
The answer is yes. The answer is yes. It's a secondary effect due to the fact that this kind of beta azopolymer perform cis to trans change, and they release energy to the matrix. So the matrix is heating, and this heating then change the Young modulus of the polymer. So it's not the same if you don't put inside the dopant, because we did the same in the same polymeric structure without the doping, and we didn't have the same increase of temperature. So it's basically very important to have this kind of dopant. But what is important for us is the fact that these thermal effects are very well localized. And this localization is due to the fact that you can induce in a very small part of your sample the laser illumination. And also because the polymer doesn't in the polymer the heat doesn't propagate due to the property of thermal property of the polymer. So remain very very well localized on the single so it's true that is thermal, but you can't have the same effect only changing the environmental conditions, and this for us is very important.
May I just ask, when you add this beta, is the color of your polymer changing a lot?
Yes, you mean if we put just a DIN inside and with the same color, it's absorb the radiation. This is true, but not the same. The effect is not the same.
But it has an absorption peak in the blue, right?
Yeah, in the blue. Yeah. This particular, we can also change the dopant. There are different dopants, and you can use also green light, and with there is I can't remember exactly the name of this dopant, but it's yes, it changes the peak of absorbing the absorbing peak.
Okay, thanks.
Okay, thank you. Thank you, Marco, also.
So, is there any other question? So, if not, maybe let's thank our speaker again. Thank you for the nice talk, and thank you for your time.
Thanks to you for listening and insightful discussion.
Okay, one last comment. Next week will be Martin Wegener. So our next webinar speaker in a week time at the same time. Okay, thank you all for coming with us today.
Okay.
Thank you. Let's meet next week. Bye-bye.
Bye. Thanks again.
Bye-bye.
Bye.